前世もありがとうございます。
こんにちは。よろしくお願いします。楽しみにしています。
よろしくお願いいたします。どうも。Okay, it's time to start the seminar today. So today we have a guest from in India. So the speaker is Vikrant Kumar. He's from the TCG CREST, Calcutta, and he will be talking about the very interesting chemistry application of quantum annealing, electronic structure calculation using quantum annealer Eigensolver. So please, and by the way, so you have a 20-minute talk and roughly 10 minutes discussion time. So please start.
Okay. So hello everyone, my name is Vikrant and I'm going to present a seminar on the topic electronic structure calculations using the Quantum Annealer Eigensolver. So this seminar is based on our recent preprint on the title Accurate Computation of Relativistic Excitation Energies using Quantum Annealing. So these are my collaborators. And so I'll quickly just, I think people here know what quantum annealing is, what adiabatic quantum computation is. So I'll directly skip to the algorithm, the Quantum Annealer Eigensolver. So this was proposed by Teplukin et al. At Almost National Lab. And the idea of this algorithm is that we have to map the eigenvalue problem at psi equals E psi to a minimization problem. And we do so, and we use the specific minimization problem of the quadratic unconstrained binary optimization. Why do we use that? Because the quantum annealing process in D-wave systems, the final Hamiltonian is the longitudinal Ising field Hamiltonian. And so that allows us to convert to solve QO problems on this type of systems. So the idea here is that we set the energy of a molecule as the expectation value of the Hamiltonian. And then this wave function, we represent it in a suitable basis of size B. So this equation is then expanded, and then now you can see that this looks similar to how the QO is written. So both of them are quadratic in the variables, assuming that H alpha beta is computed through a classical routine. So here there are two problems. First is that the xi's here in the QO are discrete. They are actually binary, whereas the expansion coefficients are continuous. So to make this mapping, we use a fixed point representation so that we can convert a fractional number to a binary string of bits. And these bits will be computed using the qubits. So next, we will impose the constraint that the psi is normalized so that we have the equation psi at psi minus lambda psi psi, and this we have to minimize using the quantum annealer. So this gets converted to this form, expanded in terms of the expansion coefficients, and then it gets mapped to the QO problem. Okay, so to give a bit more detail on the algorithm, I will just go through the steps. The first step is you will compute the Hamiltonian matrix elements. Then you will initialize lambda to some positive value and assign a number of qubits to each expansion coefficient. Then you will construct the QO, and then you will sample the QO on the quantum annealer. And then after you obtain many samples from the annealer, you will, among all of the samples, you will check which sample gave you the lowest energy of the system. And that you will use as a guess for the next lambda that you will use to update your value of lambda. Here you have a Lagrange multiplier to keep the psi normalized. And then you will construct a new QO, and then you will keep doing this until you reach some kind of a stopping criteria or convergence. And then you will pick the lowest, the best solution among all the solutions that you got. And that you will say is the energy of your system computed through the QAE method. So the problem here is that the molecular Hamiltonians can be very dense. So we have seen from our calculations that even if we have just 18 coefficients, so it gets converted to 5,000 qubits on the D-wave quantum annealer. So that's a huge number of qubits required. So to solve this, D-wave has recently proposed hybrid quantum annealing. So I will just give you how this hybrid quantum annealing works by giving an example of the QBSolve workflow that they have provided on their software packages. So here, the first step consists of you initialize all the variables to 0 randomly, and then you use a classical sampler to search for a minima. Then you will compute the impact of each of the bits to the QBOS energy so that you can order them in that order, and you will start optimizing them in chunks in that order. So in the iterative optimization step, the first step is that you will sample the QBO through decomposition and embedding techniques. So here, that step I have shown here in this diagram. Here, the first is that you partition the QBO into sub-QBOs. So this partitioning, so you can represent the QBO using networks, and these highlighted bits, this can be a strategy that you can choose to select a few nodes of the entire network, and you choose to optimize just those nodes, and you keep the other nodes frozen. So you can employ many different strategies on how you wish to choose these nodes, and by using a appropriate strategy, you can divide the cubo into subparts, and you will optimize each subpart in a different iteration. And next, after you have chosen a subpart, subcubo, you will embed it on the quantum annealer using chains and all, and then you will perform sampling. So if you perform many samplings, then you hope that one of the samples will return you a good sample that will have energy that is near the global minimum. So here, from now on, I will mention this sampling process as a repeat, and each repeat will consist of 1,000 anneals. So next, we will update the solution with the subsample, and we will keep doing this process until all the subcubos have been optimized. And then after we have got a solution, we will search for a minima using a classical sampler, and then we will check if the result leads to an improvement. And then we will create a new order of the impact of each variable, and then we will keep on doing this iteration many times until it leads to a convergence. So here, after substituting the method, the sampling of qubits using quantum annealers through hybrid quantum annealing, we can solve even bigger problems. But here the problem is that we are also using a classical sampler in conjunction to a quantum annealer or a simulated annealing. So here it is difficult to assess like how much improvement does a classical sampler is giving you and how much improvement are you getting from the quantum annealing step. So to do that, so to just assess that, I've just made changes. We have just made changes to this workflow, and we have removed the classical sampler part and just checked if we just use the simulated annealing, how much results can we get. So here I've shown two systems. One is H2, the cubo size is 40, and we break it into 4 subparts, and the accuracy with respect to the FCI calculation we get is 10 to the power minus 6. But the total number of repeats that we have to do is 300. Again, for the HF molecule, we have a cubo size of 360. We break it into 9 parts, and then we will get accuracy of 10 to the power minus 2. And the number of repeats increases by a lot, 2200. So this is very low, and even the accuracy for HF was very low. So now I will explain what our work is. So I will first demonstrate our improved hybrid quantum annealing workflow. Then I will show the results on some molecular systems. Then I will show how we can compute excited states, but using a different method of employing the atomic symmetries. And then I will apply our workflow for the computation of relativistic effects using this quantum annealer eigensolver. So the improvements of the workflow are broken into 4 parts. First is we employ a floating qubit encoding method that allows us to get more precise estimates of the coefficients without expanding more qubits. Then we have a perturbation theory based qubit decomposition that allows us to order the coefficients in a more optimized way, so that we do not have to keep on computing the impact of each of these variables every step, but just do it once in the starting and use that for our subsequent iterations, and that will lead to lower iterations when compared to the previous methods. And then there are some optimized embedding and post-processing strategies. And then finally, the way we optimize lambda, we do it self-consistently so that the number of iterations is reduced even further. So I will just go through the steps of the workflow, and I will explain each of this part as I go through them. So the first step is that we construct the Hamiltonian. Then we initialize the variables. By initializing variables, I mean that we start with a guess wave function of the Hartree-Fock wave function. So A0, that is the first dominant configuration, that is set to 1, while all the other expansion coefficients are set to 0. And the value of lambda is set to the Hartree-Fock energy. And then we sort the expansion coefficients using perturbation theory. So here, basically, we assume that the next configurations, they are a perturbation to the most dominant configuration. So here, from first order perturbation theory, we have this equation. And if you substitute n as 0, that is all the next coefficients are a perturbation to the 0th configuration, we have this formula. So we compute this order of all the expansion coefficients, and then we optimize the variables in this order. So next we have to do is we have to construct the cubo, because we have to convert each of the expansion coefficients to binary string. So to do that, instead of using the fixed point representation, we have developed a different method. That is, we use it using some mode that is a floating qubit encoding. So here the idea is that A alpha, the expansion coefficient at any iteration I, is represented using mu alpha plus sigma alpha into sum over something that is very similar to the fixed point encoding. But here what happens is that mu alpha at any iteration is the result of our previous iteration. and sigma alpha keeps on decreasing. It's a weight that we assign to the result that we get from the quantum annealer. So what happens is that the quantum annealer has to predict these q, k alpha values such that a alpha gives a better solution. And since the weight is decreasing every iteration, the quantum annealer is basically letting us compute the correction to our previous estimates of the expansion coefficients. So by this, even if we use 10 qubits per expansion coefficient, by this decrease, because of this decreasing sigma alpha, we are able to compute more precise estimates of the coefficients. So next is that we choose a subset of configurations. So basically choosing a subset of configurations means that if we, let's say, have only 40 or 50 qubits per iteration to give to a calculation, then we will choose corresponding L number of dominant configurations that we can afford to do in a iteration. And if you combine this method and the first step, you basically I can basically say that our method is doing something like we compute the coefficients of the first L dominant configurations, and then we compute the next L dominant configurations, and we keep doing it until we have added all the dominant configurations one by one. And then after all of them are added, we will now compute the correction to our previous estimates. And finally, the embedding process that we actually change the way change strengths are determined, and that's alpha times RMS of the quadratic biases and some post-processing strategies. And in between, we have the sampling on the QPU that gives us many samples, and among them, we choose the best one. And for updating lambda, the previous methods used to compute lambda by varying over a specified range of lambda or by using the method of bisection. Here in this method, what we do is that we use the theory of FCI. That is, if you recall, the equation that we wanted to minimize was epsilon equals psi h psi minus lambda psi psi. So from FCI theory, if you minimize epsilon, and so then you get the FCI equation HC equals EC. And from there, you realize that lambda is actually equal to C. So this allows us to use the self-consistent method for updating lambda. That is, you select an approximate set of coefficients and energy, and then you use an iterative method to obtain more accurate sets of coefficients. And then when this method converges, you stop updating lambda. Okay, so the results. I've shown the results on 5 molecules. The first method was done HF. The first method was done using FCI, and I will show how our workflow gave to the improvements. So in the 0th iteration, we start with the case of Hartree-Fock energy, and our workflow slowly, as you can see, improves our estimate of the result. So here, these solid lines, they actually show the result from every iteration, versus the dashed lines are the ones that we are taking. That so basically, it's the lowest value till that iteration. That is because we only choose those results that are improving our results. So dashed line basically depict what you would get from the workflow if you were to stop the result at that repeat. So here error means E minus the FCI value, and these are actually runs for 3 different jobs. And next, the other molecules, since they were very big, we use a CISD method. And here we optimize the first 20 or first 30 dominant configurations in the starting, and then we optimize the next smaller order coefficients. So for these systems, as you can see that here the accuracy versus the Hamiltonian size is almost the same. Actually, it's the green line. So it's almost like around 10 to the power minus 3 minus 4. Whereas the number of iterations that we require to converge, it increases linearly. So, but still, this is linear and not exponentially increasing as you would expect. So this is a good news. So here, just to remind, the results that we got previously from QB-Solve's method required us 2,200 repeats for just the HF molecule, and the accuracy was also till 10 to the power minus 2. So next, I will finally talk about how we use this method for computing excited states by taking advantage of the atomic symmetries in the case of atomic systems. So here, in the same case, we have epsilon equals psi minus lambda psi, and the wave function is expanded in terms of the atomic basis sets. So now one difference between molecular systems and atomic wave functions and atomic systems is that in atomic wave functions, their basis sets can be uniquely identified by the total angular momentum, magnetic quantum number, and parity. So the wave function and the eigen basis, they are eigen functions of the J square, JZ, and pi operator. So the idea is that we divide the wave function basis into 2 parts. One basis consists of J equals half, and the other consists of J equals 3 half. And from these different bases, we optimize the we perform optimizations or the QA workflow in the basis with J equals half only. So from that, we will get the energy E halves, the energy of the J half state, and we will get the energy E 3 halves, that is energy of the J equals 3 half state. So by using this, we can compute the fine structure splitting for boron-like ions. This is a purely relativistic effect, and this has been the first time someone has calculated the relativistic effects using the quantum annealing. So to do this, we actually need to use the Hamiltonian that is relativistic in nature. So here we use the Dirac-Coulomb Hamiltonians, and to that we add the bright interactions so that we can further improve upon the results. So by using the Dirac-Coulomb bright Hamiltonians, by computing them through the relativistic atomic structure package called CREST2, we perform these calculations for two sets of states. One is 2p half and one is 2p 3 halves. So the 2p half problem had a cubic size of 90, and the other problem had a cubic size of 160. So, and the total repeats that we required is 30 and 45. So in basically 75 repeats, we are able to compute both the states, and the accuracy, if you would just check. So RelCI actually means the results that we get from classical computations, and simulation is basically performing QA using simulated annealing. SD is the standard deviation by performing these simulations for 5 different jobs, and SD in hardware is the result by doing QAE on actual DWF advantage 5000 qubit machines. So as you can see, the agreement with RelCI is quite good. Like it's to the 10 to the power -3 or -4 level. So and you can see that how this accuracy is changing with respect to system size. The error slightly increases as the system size increases. So finally, by taking the difference, we get the fine structure splitting, and these are the RelCI values. This is the percentage fractional difference in simulation and hardware. So one thing to note is that the difference between simulation results and hardware results is not very much. They are so unlike gate-based quantum computing, here the difference hardware errors is actually quite less. So and when we compare these two results with experiment, you will see that the percentage fractional difference is like 0.04% or 0.14%. So the accuracy is, I think, quite good. And this difference, this less difference between simulation and hardware is something that was also observed in scientific reports of the original QA paper. So to conclude, we have made improvements to the quantum annealing eigensolver workflow, and we have implemented that for both molecules and atoms. When we use quantum annealer eigensolver with simulated annealing for molecules, we have shown that we can significantly reduce the number of quantum anneals required to obtain the ground state energies of light molecules, and the scaling is now linear with system size. And we have also improved the accuracy of QA calculations without expending more qubits. And then for atomic systems, we have provided DWave results, and these are the first many-body computations using quantum annealing. And for the fine structure splitting, the agreement with classical calculations was still an accuracy of 10 to the power -4, and with experiments it was 10 to the power -2. Thank you.
Okay, thank you very much. Very, very interesting talk. So I'm really impressed. So, okay, any question, comment from audience? So if you have a question, yes, okay. Nishimori-sensei, please.
Thank you very much for the very interesting talk. And I have a few questions, and I ask them one by one. And in the first part, you formulated the eigenvalue problem as the minimization of some sort of matrix like quadratic quantity. And you introduced the coefficient h sub alpha beta. And I wonder, I'm not an expert in this field, so I ask a very naive question. Is it easy to calculate this h sub alpha beta for a given phi alpha and phi beta?
Oh, so do you mean this phi alpha h
Yeah,
beta?
yeah.
Oh, yes. It is not very easy to calculate that. But as compared to, I think, as compared to getting the eigenvalues, it would be of similar level. But it's definitely not easy. That would be for sure.
Wow. So for a very big problem, you have to consider a very ingenious method to calculate this quantity.
Mm-hmm. Yes, that is true.
That's a problem. Okay. Another question is the following. You want to minimize this function E, the energy, and you express this continuous variable A alpha and A beta in terms of a binary representation to map the problem into a cubo of the Ising type. But is it possible to directly minimize this function E with an algorithm for continuous variable optimization? This field is very well developed. And is it better to use the quadratic or cubo form than to optimize directly by the continuous variable algorithm?
But do you mean like using quantum methods?
Or classical?
Classical.
There are a lot of classical, good, very efficient classical methods to minimize this quadratic form for
yes. Regarding the comparison of the complexity of using quantum annealing for solving this cubo form versus using a classical method for optimizing a continuous variable quadratic equation.
Yes.
In that,
they are very strong generally.
Oh, so that I'm not very conversant with the comparison of their complexities, so I'm not able to comment on that.
Not just about the mathematical formulation of complexity theory, but you may be able to test numerically by using those algorithms. There are a lot of packages. So may I ask you a final question? It's about the further improvement of your approach. You at the final part, you mentioned that this method, the accuracy of this method approaches other good methods. And is it any prospect that this method will achieve better results than any other methods, classical or quantum, in the formulation of cubo?
I am not sure again about that. So that will require some extensive understanding of how well the quantum annealer is able to give you the results, like how fast is it able to give you the results, and how much accurate are they. So in that, I am not very conversant, like how good a quantum annealer can work in the future or presently. So that will require an understanding of that.
Okay, thank you.
Thank you.
Okay, so any other questions or comment from audience? So please use raise hand button in the bottom of your screen. So
Shiro, I see there is something in the chat. You should take a look at the chat.
Chat. Yes. Okay, yes. Okay, I'd like to respond to some senses. Okay, yes. Yes, please. Dr. Das?
Yes.
Yes,
hello,
please.
Hello, Nishimori Sensei. This is Bhanu Das. Yes, I'd just like to respond to your first comment.
Thank you.
Is about you asked about the calculation of the matrix elements of the Hamiltonian H, right?
Yes.
Now that is done classically. That is the classical part of the computation. So Vikrant, can you just show the go to the relativistic Hamiltonian? Yeah. Yes. Okay. So Nishimori Sensei, what we do is that we, since these are sort of electrons, we use the many electron Dirac equation, the many electron Dirac Hamiltonian, which is given in this slide. And to this we add what is called the bright interaction. The bright interaction is the relativistic correction to the Coulomb interaction, the leading order relativistic correction. So that is absolutely important because this is a relativistic effect. The fine structure splitting completely goes to zero in the non-relativistic limit. So that has to be added. So once we do that, we have the total Hamiltonian HDCB, which is the Dirac-Coulomb part, plus the relativistic correction, which is the bright part, you see. Now, without the bright interaction, we cannot get the kind of accuracy that we've got. We've got about 98 to 99% accuracy. I think without the bright, it would be much less. Then what we do is that the wave function corresponding to this Hamiltonian, Vikrant, if you can go back, please. I mean, yeah, you can stop here. Yeah. So you see the wave function is psi, which is an atomic wave function that we expand in terms of different configurations, that is the phi alpha, which consists of the mean field term and then corrections to it, one particle, one hole, two particle, two holes, three particle, three holes. Now, in this particular case, we took all particle hole excitations, which is, 5 particle, 5 holes. So you see, yes, so this is the expansion for psi in terms of the various basis states. And the basis states are built out of single particle wave functions, which it's a sort of a multi-configuration kind of a single particle orbitals that we construct. So we first construct orbitals for single particle wave functions, and then we build the phi alphas, which are the many electron basis functions. And then the Hamiltonian that we saw, the Dirac-Coulomb Hamiltonian, we calculate the matrix elements of that Hamiltonian corresponding to the n particle n hole wave functions that are shown here. So this is done on a classical computer. It takes a lot of time. I mean, we've done this on Subame, for example, quite a few times. And so sometimes it's necessary to parallelize the codes. And these are done fairly efficiently these days. Maybe about 30, 40 years ago, they were not so efficient. But this part of the calculation is particularly efficient, especially for a simple system like boron, which has 5 electrons. So that's what I wanted to say.
Okay. Thank you. I understand.
Thank you.
Okay, Dr. Das, thank you very much for your explanation. So any question or comment? Okay, we can accept a couple of questions. Still, we have 3 minutes. Okay, I have a very simple question. So your workflow, it can be applicable to the NISC processor, like the IBM or something. So your strategy as well, so can be applicable to the NISC quantum computer and give some advantage.
Oh, I was muted. Oh, actually, yes, I think about the advantage. I think some parts may be adapted for solving on these computers, but about the advantage, again, I'm not very conversant with how this advantage thing really works. Like, what parts can give advantage on next processors, what parts cannot. So regarding that, I am not very conversant with.
Okay, thank you. So, any question or comment? Okay, if not, let's close the INQA seminar today. So thank you very much, very interesting.
Thank you everyone for coming.
Let's thanks to the speaker again. Yes, thank you very much. Yes. Okay.
Thanks to the organizers for organizing this. Thank you.
Okay, see you. Bye.
It was very nice. See you.
Bye, everyone. Yes.